All right, so we're opening to page 21, and while we're doing that, I just want to apologize for some homework that I should not have assigned. Number 31 and number 25, part C, I should not have assigned because we don't have the tools yet to solve those two questions. So apologies, it's my fault, but it is a function of the updated edition of this textbook. And some of the ordering of the trig stuff has changed quite dramatically from last time I taught this course. And so I assigned some things without realizing we didn't yet have the tools to do them. Sorry about that. Okay, our look at the calendar. Today, project number 5 is due, so hopefully it's in the folders. Project number 6 is officially assigned. I have extras up here, but I handed them out last time. Is there anybody that does not have project 6 from Wednesday? All right, so today we talk about graphing sine and cosine, and then this funny word sinusoidal functions. So let's go ahead and get started on the bottom of page 21. And for some folks who came in late, some of us were playing with this game called Lights On or Lights Off. So, so if you go Google that phrase, you can play, and we haven't yet solved this puzzle, but if somebody wants to spend some time over break playing around, that would be great. Okay, so we're on page 21. Can we go to Sarah for number 1 in the middle? Oh, actually, we're going to skip ahead. Number 2. Okay, so the goal for the first part of this class is to fill in more stuff on the unit circle. And we have this triangle that we've talked about already. Don't copy this part down just yet, but 1 and a 1 and a radical 2 were the sides that we had figured out for the 45, 45, 90 triangle. But our unit circle has what as the radius? Has a 1, and this one has a radical 2. So what I'd really like to do is force that to be a 1. And the way to force that to be a 1 is to divide it by radical 2. But if I divide one side of a triangle by radical 2, I better divide all the sides by radical 2. So maybe this is something we can copy down on the sides. The legs are 1 over root 2, and the hypotenuse is a 1. And now we can go back to our unit circle, the one that's starting to get filled in. It's this one here. So go back to page 14. And ultimately our goal is to fill in all of the coordinates of the points. And within the next 2 minutes, we'll have the tools to fill in all the coordinates of all the points. But we just figured out the one with 45. So don't write this in because it's going to clutter the picture up. I'm going to erase it momentarily. But if I consider that triangle right there, okay, clearly it's a right triangle. How much is this angle over here? 45, because it's the 45-degree point. And so we just figured out, well, let's see, how much is the hypotenuse of this triangle? This is a 1 because it's the radius. But we just figured out that that particular triangle has a 1 over root 2 down here and a 1 over root 2 over here. So how much is the x coordinate, which is the horizontal distance? It's 1 over root 2. And how much is the y coordinate? It's also 1 over root 2. And then what we can do is we can fill in some other points that are just like this 45, but are in different quadrants. So for example, if I go to the 135 line, that's the one in the middle over here, and I wanted to know the x coordinate, which is this number down here. So how long is that? It's negative 1 over root 2, isn't it? It's the same distance as it was over here. same distance, but it's negative. We're going left. So the x-coordinate here must be negative 1 over 2. And then the y-coordinate, which is this length, that's positive or negative, is positive because it's up. So that's 1 over root 2. Any questions on that? All right, we'll leave it to you guys to later on fill in the other two that are downstairs. But let's go back to the other triangle on this page. It's the 30, 60, 90. Okay, don't copy this yet because we're gonna fix it. But here are the numbers that I have memorized for this triangle. It's a 1 and a 2 and a radical 3. But I'm not thrilled with that. How much do I want the hypotenuse to be? I want the hypotenuse to be 1. I want that triangle to squeeze into my unit circle. So let's change it. I'm going to divide everything by 2. So this 1 over here becomes 1 divided by 2. That becomes root 3 divided by 2. Let's get those numbers copied. And then I think we'll be able to fill in some more stuff in our unit circle. So we'll go back to page 14. Not 14. Where should I be? There we go. Okay, so back on 14. And then we're going to fill in. And again, I'll erase this, but taking a look at that triangle right there, how much is the angle? That's 30, so that is the 30, 60, 90 in the same orientation that we just saw it. How much is the hypotenuse? 1, that's the only reason we fit it into this unit circle. How much is the bottom leg? That's a root 3 over 2. And how much is the vertical? That's a 1/2. And so then we get to start filling in more coordinates. What is the x-coordinate of that point? This is root 3 over 2. How long is it going left, right? That's radical 3 over 2. How much is the vertical? It's 1/2. Okay, so I'm going to erase that. I'm going to ask you guys to find the point in the second quadrant that's just like this 30-degree point, and see if you can label the coordinates of that one in the second quadrant. All right, so which angle in the second quadrant is like the 30-degree angle? Is this 150? And what can you say about the x of this 150 point? It's going to be negative of that radical 3 over 2. And how does the y compare to that y coordinate in red? It's the same, it's positive. Okay, I trust you guys could fill in the symmetric partners downstairs. So which are the angles that are still left up here? 60 and 120. Well, we can still use the same triangle. I'm going to draw this way. How much is this angle in here? That's 30. And that makes this angle up here that I don't really care about. That's my 60. So it's the same triangle, but the sides are just going into different spots. So how long is the vertical of this triangle? That's the root 3 over 2 now. And is that root 3 over 2, is that the x or is that the y? That's the y. That's how high we went. So the y coordinate there must be root 3 over 2. And the other side of my triangle up here at the top is a 1 over root 2, and that must be the x. Oh, sorry. Of course, it's 1/2. Questions on that? And now we know everything in the first quadrant. All those points are labeled, so you can just do the right thing and copy them down with pluses or minuses in all the other quadrants. So we'll leave filling in the rest of them for an exercise, but it is all filled in on the first page. I think there's something to be said for kind of filling it in on your own, but you could at least confirm and now maybe understand where all these mysterious numbers are coming from. All right, so something else I want to say here in terms of kind of remembering stuff. So on every quiz and every test that you are doing trig stuff, you will bring the first page of this packet, which is the completed unit circle, okay? So I'd like you to be able to use that unit circle. But in terms of remembering stuff, like if you're walking down the street one day and somebody says, hey, quick, how much is the sine of 30 degrees? I want you to know. And so, so my friend Niels, we've showed a couple of his PowerPoints and his Excel stuff before. So he has a really nice way. I think it's really nice to think about like what these numbers are. So first, let's take a look at the numbers that I'm going to circle here in purple. 1/2, 1 over root 2, radical 3 over 2. And first recognize that those are the only numbers that appear anywhere on the circle in the X or the Y, excluding the 1s and 0s, right? Like those are the same 3 numbers in the Y's, but they're in different spots, right? I mean, that radical 3 over 2 is now up there, and this 1/2 is now down here. And that guy is the same as that guy. So there's only 3 numbers that we're playing with. It's really just a matter of knowing where those numbers live. And so first thing Neil said is, so he didn't really like this idea, like these numbers didn't really seem natural. He couldn't find a pattern. 1/2, 1 over root 2, radical 3 over 2. So here's what he did. He said, okay, the 3 numbers we're playing with here are 1/2, root 3 over 2, and 1 over root 2. So first thing he says is, well, I see 2 denominators that are the same. They're both 2's. Let's do something to that last one to make it a 2. What do we do to the last one? Okay. We can't square it without changing it. Yeah, this is where we can rationalize by multiplying by the foo-foo radical 2 over radical 2. I don't need you to do this in general, but this is Niels' way of at least trying to make them more similar. So what are the denominators now of my 3 things? So we've got 3 2's in the bottom, yes? And then he saw more patterns. He said, well, let's see, on the top, there's a radical 3, and on the top, there's a radical 2, and on the top, there's a 1. But of course, he said, well, let's think of that as a radical 1. And so for the first time, and maybe last time in your math career, I'm going to ask you to not simplify the square root of 1, but leave it as the square root of 1, because then the pattern is there. So, okay, Neil said, here are the 3 numbers, radical 1 over 2, radical 2 over 2, radical 3 over 2. Very clear pattern between those 3 numbers. And then he said, well, let's go ahead and think of these numbers as being small and medium and large. Clearly, that's the order that those 3 numbers are in, right? Small, medium, and large. And then the only other thing you need, once you understand those are the only 3 numbers that are on the circle, is to just kind of figure out, well, which one are you at? So let's go down to one of these that we haven't labeled yet. Suppose we go to right here. And I'm going to go ahead and draw in my right triangle. So there's a blue, and there's a green, and here's my right triangle. Looking at blue and green, your choices are small, medium, and large. In fact, let me do one other thing first. I'm going to draw that blue, and I'm going to draw that blue. Do you see the small, medium, and large? It's pretty clear which one is which, right? How much is the far left? What number is that? It's a small. It's a radical 1 over 2. How much is the medium? Radical 2 over 2. How much is the large? Radical 3 over 2. You guys just filled in the y coordinates of these points. They're all negative, so put negative in the front. But those are the 3 y's, small, medium, and large. And then going the other direction. Okay, drawing that green up there maybe is not as helpful. Let's draw the green over here, and let's draw the green here. Let's draw the green here. Do you see the small, medium, and large? So how much is the top green? What number is that? That's root 3 over 2. It's large. And the middle green, root 2 over 2. And the bottom green, root 1 over 2. And so you are right now filling in without reference to any fancy triangles or really a whole heck of a lot that's memorized. You just filled in the 3 x's. And they're all negative because we went left. I want to give him credit. He's the one that showed it to me, so I'm giving him credit for showing me. What's that? I don't know. Okay, so anyway, however you can do it, I'd like you to be able to get to a point where you understand like that there's not just random 800 different numbers on here. There are definite patterns. There are ways to figure out what these numbers are if push comes to shove. Tassiday, did they talk about small, medium, and large in the book? Mm-hmm. Okay. All right, so let's go to page 22. Number 4, and we'll go to Vance. Okay, so let's give this a shot. I'm going to write down a few things. Sine of 0, sine of 30, sine of 45, sine of 60, and then finally sine of 90. We're just going to do the first quadrant stuff, and then we'll use the patterns, symmetry. Okay, thinking about the unit circle, is the sine the x or the y? Sine is the y. You guys look at the unit circle, go to the 0 degree angle, and grab the y coordinate of that point. What is the y coordinate of that point at the far right? That is a 0. So sine of 0 is 0. Now go to the 30 degree angle, grab the y coordinate. What is it? 1/2. Root 1 over 2. I'm actually going to go decimals for all of them, so we'll do that. Sine of 45, grab the y coordinate. That's root 2 over 2, that's the medium. On a calculator, root 2 over 2, which is around 0.7. Sine of 60, the y coordinate again, is root 3 over 2, which is around 0.866. And then sine of 90 at the top is a 1. Okay, so as I stand here, I realize I put degrees, but what should I have been putting? Right, and given the picture that I'm trying to fill in, okay, no problem. You guys have erasers, right? Okay, 0 radians, pi over 6, pi over 4, pi over 3, pi over 2. All right. So now we're going to plot some points. The x is there. Y is whatever we got as our answer. The input is the angle, and the output is the sine of that angle. And maybe part of the difficulty here is that pi over 6, pi over 4, pi over 3, we have to find them on this new graph. It's no longer like an angle rotation graph like the unit circle. But let's see if we can't find them. So first of all, what number is right there? That's going to be pi over 2, right? That's half of the pi that's sitting there. So then what number is there? That's pi over 4 by cutting it in half again. Okay. And now I feel like I have a sense of where things are. So let's start plotting. The first point, what's the input and what's the output? 0 and 0. All right, so the graph of this new function, y equals sine theta, hits the origin. Great. I'm going to jump down to the last point. Sine of pi over 2 is 1. So pi over 2 goes up to 1. So we go to pi over 2, we go up to 1. So we're going to hit those 2 points. It's just a question of how we do it. Okay, pi over 4 is here in blue. What's the y-coordinate supposed to be? It's 0.7, which is interesting because if it was going to graph a straight line, what would the y-coordinate have been? Should have been 0.5 if I was going a straight line, right? Halfway between, should get to halfway between 0 and 1. Okay, apparently sine is not a straight line because when I'm halfway between at this pi over 4, I'm up at 0.7, which is closer to the top. And then we're just going to ballpark the other 2 points. Pi over 6 is a little bit smaller than pi over 4. Do you guys remember how in the unit circle, the first rotation was 30, but then how much was the next rotation? It was only 15, right? It was 30 and then 15. So the pi over 6, it's not halfway. It's pretty close to the pi over 4. So pretty close to pi over 4. What's the y-coordinate supposed to be at pi over 6? Is a half. So relatively close to pi over 4, we're at a half. And then on the other side of things, pi over 3 is not that much bigger than pi over 4. And I'm supposed to be up almost at 1 at 0.866. So maybe something like that. And so I'm just going to connect these with some smooth curve. And we've got the beginning of our graph of sine of theta. And then let's think about what happens. I've just passed pi over 2. Can you guys point which compass direction is an angle of pi over 2? Everybody's pointing. Which compass direction is pi over 2? It's up, right? It's north. So I've just passed north. So now we're swinging into the second quadrant here. Are the signs of these things positive or negative? They're still positive because they're the y-coordinates, and the y's are still positive because we're up above the x-axis. So I'm still positive. In fact, I'm the same numbers that I was on the other side, right? We had all these symmetry type things here. So it's going to be the same picture, but instead of going up, it's now going to be going down. And in fact, we're going to hit this point because that's the one that's like the 0 point. And so I'm not going to plot any more points. Well, maybe a couple more, but I'll just sort of confidently say it's going to look the same just on its way down. Now we're sitting at an angle of pi. Can you guys point which direction is pi? So pi is this way, it's west. And once I pass that, I'm now rotating downstairs to quadrant 3. What kind of y-coordinates do we have down there? We have negative numbers. So it's going to continue. It doesn't do anything dramatic. It doesn't all of a sudden say, oh, we're just going to bounce again. It continues. It was gently going down towards the negative, and it does that. And let's, I said I wasn't going to plot any more points. I'm just going to plot 2 more. So let's go right here. What angle is that? That's halfway between pi and 2 pi. That's 3 pi over 2. 270 degrees is good. And so it's going to continue. And eventually when I get down there to the straight down point, what's the y-coordinate? It's -1. So when I get to straight down, 3 pi over 2, I'll be at -1. And so we're continuing on with our curve, and it just kind of smoothly gets down there, ready to turn around. And then finally, if I get back to 2 pi, which direction is 2 pi as an angle? 2 pi is back to the beginning, it's east. What's the y-coordinate of that point way out there? It's 0 again. So we're going to hit this point right here. And we will draw the ending part. And that's a graph of y equals sine of theta. Questions on what we did there? Doesn't look too surprising because we've graphed stuff like that recently. What example? It was like a word problem we did where we graphed and it looked like that. It was a Ferris wheel. Remember we were looking at the height as you ride around on the Ferris wheel, and we drew something that was reasonably close to that. All right, so one thing I'll say here is that this is only one period of the sine function. once I get back to 2 pi, I'm right back where I started. We'll get another copy of the green thing sitting out here. How far does it go? Forever. If I were to rotate not counterclockwise, which is a positive angle, but if I were to rotate negatively, I'll get the same thing over on this side. So it just goes left, right, forever. There's nothing really special about the 0 to 2 pi part, but we kind of have to focus our attention someplace, and that's where we focus it. So 0 to 2 pi, and then lots of copies as far as you have the patience to draw. All right, so let's go to Kyle for 5. Okay, so here's a Sketchpad file. I did not make this one. This was by Audrey Weeks. And so there's our unit circle. Apologies, I don't think I can make it any bigger, but really you just need to see the image. You don't need to be able to read everything that's in the that's up here. So I've got this point that's on the unit circle. It's right up here, and let's think about graphing the sine function. Is the sine function the x or the y? Sine is the y. What color is that y coordinate? It's red, right? We're ignoring the blue at the moment. The red is the value of the y coordinate. And so if I'm at a certain angle, that's this angle, oopsies, undo. That's the angle right in there. Then the y coordinate at that point is this red length, and the red length has been copied over. If I increase the angle a little bit, what's going to happen to that red length? It's going to get a little bit bigger, and it's going to get traced over here a little bit bigger. And if I drag this thing, so I'll put it back to the beginning. That was the original, the 0, 0 that we talked about. And then you can see as the angle gets bigger, the vertical part gets bigger. And so that red is always translated directly over to here. And then what happens when I pass 90? I pass pi over 2. It's going to start getting smaller. You can see that the red is just, it's reached its peak at 1, and then it gets smaller. Now what's going to happen when I pass? It's going to get bigger again, but it's going to be negative because now we're down here. And so that red is now just down below the axis. And so what we want to do is maybe put it back to the beginning, but actually I'd like to be able to see this whole thing. So I'll trace that point, and you get the thing that you guys just drew. No, you're not ready for that. Okay, so now I'm going to hide the sine one, and I'm going to show you the cosine one. Let's bring this back over to here. Okay, cosine, is it the x or the y? Cosine is the x, so I'm just going to bring the x coordinate in, which is not shown here, but there it is, the blue, dark blue, right? So that's the x. It's a little bit weird now because that horizontal blue line has to get translated because we're trying to graph y equals. Okay, so there it is. And we're just going to get a different kind of graph, but it's the same idea. At the beginning, what can you say about the horizontal length? How much is it? It's going to be 1 at the beginning, and then it's going to get smaller. And at the top, how much is the horizontal length? It'll be 0. And then what happens to the horizontal? Now it's negative. Okay, so let's trace this guy. I actually like to trace the line instead of the dot. I think it looks cooler. So let's try that one. Yeah. Your reaction is not big enough. I'll give you another chance. Yeah. Okay, so the red thing is the graph of sine. The blue thing, which is kind of shaded in, is the graph of cosine. And they look quite similar, maybe just shifted a little bit. What's that? Out of phase is the engineering way to say it. Okay, so that's good. Some properties real quick here. In fact, so quick, we're going to skip them. Let's go to number 7. Chris. Okay, so we're just drawing, and with practice, you can draw this thing right quick. We'll put 2 pi somewhere out there, which means pi is here, which makes this pi over 2, and this one 3 pi over 2. At the top, we have 1, which is about 1/6 of the horizontal. At the bottom, it's -1. I'm going to plot 5 points. Sine starts there, bounces up through the middle, bounces down, and hits at the end. And then finally, we connect the dots in some smooth curve. How much was that? That was not more than 30 seconds.
I got you at 30 right now.
Yeah, we're good. We're good. Okay, questions on that? Okay, so let's go to 8. Where are we now? We'll go to Richard. Okay, so we're not going to look at it now, but part of the questions of the day was about if you have a function, how would you shift the graph up 5? How would you horizontally compress it by a factor of a fifth? All that transformation stuff we can now apply to our 2 new functions. So, so there's cosine just for reference, and there's sine at the bottom. And really, the only thing that I know about these to like figure out which one is which is that sine starts, I say that with quotes, at the origin. And where does cosine start? It starts up at 1. It's like all that I know about graphing sine and cosine. And then I just draw the same thing, just, up, down, up, down. Okay, so let's see if we can't transform these guys to come up with new functions. And the nice thing about the reason why we're transforming these guys is that there's lots of things that go up, down periodically, right? Like I think maybe we've looked at examples of like the depth of the ocean, like at low tide versus at high tide. And it's one of these things where it just goes up and down periodically. The likelihood that the depth of the ocean at low tide is exactly -1 and at high tide is exactly 1, and it happens that it takes exactly 6.28 hours for the whole cycle, it's pretty low, right? I mean, like nothing does exactly that. But if I know high tide is supposed to be 12 feet and low tide is supposed to be 7 feet, maybe I can transform this thing to make it, stretched and shifted and moved in such a way that it looks exactly like the ocean tides are supposed to look. So that's the goal. We'll try number 10. Kate. Okay, so let's try this one. We're going to first draw our parent function underneath. What's the parent function without any fancy numbers? It's just cosine of t. Okay, so let's think about cosine of t. This will be the first time you guys are drawing cosine in this class. Does cosine start at the origin or does it start at 1? Starts at 1, all that I know. So we plot a dot right there at 1. And then the next dot is supposed to be halfway between 0 and pi. We're going quadrant by quadrant. And where does it get at the next dot? So imagine you're on the unit circle and you go to the straight up angle. And we want, yeah, it's pi halves. And we want the cosine, which is the x. How much is the x of the top point on the unit circle? The x is 0 up there. So when you're halfway, you're at 0. And keep rotating around to pi, which is due west. What's the x coordinate way out there on the left? The x coordinate is -1. So at pi, we are at -1. Now you're looking due south at 3 pi over 2. What's the x down there? It's 0 again. So we hit this point. And then finally, 2 pi has brought us literally full circle. And how much is the x coordinate out there at the right? It's 1. So this is the graph of y equals cosine t. And now we're going to look at the new function. It's 0.5 cosine of t. We're using t instead of theta. It doesn't matter. What does putting a 0.5 in the front of a function do? Makes it smaller. Smaller which way? It's like 0.5 times f of t. Yeah, this is a vertical thing because the 0.5 is outside the function. Right? If it were in the parentheses, that would be a horizontal thing. But it's outside, so it's definitely a vertical thing. And putting a 0.5 affects how tall the function is. So it becomes half as tall. All the y values become half of what they used to be. So The old y value at this first point was 1. What's the new y value? Is half. Same angle, same x. What's that? Well, this is me being efficient because I copied the same graph like every time, but okay. I appreciate that. That's just trying to be green, you know. Okay, let's see, what's for the next point right here? What's the y coordinate? It's a 0, so what's half of that? Still 0. The next point is down there at the bottom. It used to be at -1. We're doing half of it. So -1/2. Next one is here. Used to be 0. Half of that. Still 0. And then finally, this one here, you know what I should do? Because I never use that button except when my sleeve accidentally hits it. So I should just get rid of it. This last one, the y coordinate was how much? It was 1, so now it becomes 0.5. Questions on that one? Okay, task today for 11. Okay, so maybe we remember amplitude from a few classes back. It's just how far you are stretched from the middle. Normally sine and cosine are stretched how far from the middle? They're normally stretched only one up or one down. In this case, we only got stretched by half, and it's no coincidence that it's because of that half that's sitting right up there. So the amplitude is just the number sitting in the front of sine or cosine. Ultimately, we're going to have some massive formula at the end. You can see it's starting to build, like at the bottom of the screen, there's a plus k. So the formula will get more and more. Amplitude will always be this number sitting in the front of sine or cosine. Tacitade read this absolute value part correctly. If it was a negative, what if it was a negative 0.5? What would that do to this red curve? We'll just flip it right over the x-axis. But still, how far is it stretched? It's still 0.5. So just make it positive even if it's negative if I ask you for the amplitude. Oh, and I probably will ask you for the amplitude at some point. When do we have a quiz? Monday we come back. Happy spring break. All right, number 12. We'll go to Bryce. Okay, so let's try this one. Can you guys start by sketching a graph of sine of t? I would encourage you to plot 5 points. Forget the -1 there. Just regular old sine of t. See if you can plot the same 5 points that we plotted before. So I'm going to keep talking about the 5 points. Those 5 points are kind of like my base. They sort of tether me. I think it's really challenging to just draw an accurate sine or cosine graph without having a few points at least to sort of tell you what you're supposed to hit. For me, it's always those 5 points, the compass directions, right? Like you start going east, and then we have north, west, south, and then maybe copy the east one again. Okay, subtracting 1, is this an x thing or a y thing? It's x or y. Yeah, so, and depending on how you interpret this, you could answer either way, actually. If in your mind, you group the -1 with the t, then is that an X thing or a Y thing? That's an X thing. But in reality, without parentheses there, the minus 1 is, okay. Without parentheses there, the minus 1 is assumed to be outside of the sine function, not part of it. So really what you're thinking about here is an f of t and then subtract 1 at the end. And what effect does that have? Down 1. So we're just going to move everybody down 1. And I think it's real easy to do this if you've got your 5 points already labeled. Okay, so we'll go to 13, and I think we're up to Sam. Let's pause for 1 second. What is the midline of the blue graph? It's at y equals 0, the x-axis. What's the midline of the red graph? It's at y equals -1. And it is no coincidence that that is a subtract 1 there. You move the whole graph down 1, including the midline. So whatever you move at the end, that's going to be your new midline. Go ahead, Sam. Okay, so like I said, we're building up to our most general sine cosine function we can. We'll try 14 where we put those two ideas together. Todd? Sketch. Okay, so let's think about this. I first want to deal with that, that +3. What is that +3 called? There's a word. It is a shift. There is a periodic type function word. We just saw it. That is the midline. That +3 is the midline. So I'm just going to go ahead and draw in this horizontal line at y equals 3. There. And then the other piece of this puzzle is the 2. Give me the periodic type word that involves the 2. That's the amplitude. It's how far you are stretched from the middle. So all I need to do is stretch 2 from the middle because of that 2 sitting in the front. Normally, does sine start at the origin or at the top? Starts at the origin at 0. Well, the origin is now shifted up 3. So there's my new starting point. It used to be that the next important point was up 1. Now, how much is the next important point up? It's now up 2 because the amplitude tells you how far stretched you are from the middle. So we just go up 2. We're up directly above the red and blue points that we plotted second, but we're going up 2. Can you guys try to plot the other 3 points that are important, and then we'll connect the dots. Topher, do you feel any better about the use of space on that one? Good. Okay, questions on the +3 or the ×2? I'm hoping we're starting to see that like plotting points is a whole lot easier than just trying to draw the graph without any kind of basis sitting underneath. So take your time, find the 5 important points, and just connect the dots. Stephen. I might say, show me 1 period or show me 2 periods, and then you could draw 1 copy on the negative side. Yeah. I might say, graph it between 0 and 4 pi, in which case, yeah. So I'll tell you what I'm looking for. Okay. Let's go to 15. Stephen. Okay, so we've got a 1/3 times t. We know this is a horizontal. It's either a stretch or a compression. I always get them backwards, but let me show you a way to figure out what the new period is supposed to be. What's the normal period for cosine or for sine? How long does it take for us to get copies of the whole thing? 2 pi, right? You're seeing a complete cycle here. So normally the period is 2 pi. What that means is that if, for example, I'm thinking about like sine of 2 pi, then I'm really thinking about the sine of 0. Like the 0 angle is the same as the 2 pi angle. I'm right back where I started. So if I'm looking at cosine of 1/3 t, what I really want to do is figure out how can I make this thing in the parentheses equal 2 pi. We want the thing in the parentheses to equal 2 pi, because by the time the thing in the parentheses equals 2 pi, you have gone through one complete cycle. You start at 0, you end at 2 pi. I'm not saying t is 2 pi. I'm just saying the thing inside of cosine needs to go between 0 and 2 pi, and that will be one complete cycle. Cosine could care less what's happening in there. It doesn't see the 1/3 t. It just knows I'm starting at 0, I'm ending at 2 pi. That's one complete cycle. So I want 1/3 t to equal 2 pi. To solve for t, what should we do? Multiply by 3, and what do we get? 6 pi. T is 6 pi. 6 pi is the period of this new function. And so we'll tie it to compressing and stretching in a second, but if you take t equals 6 pi, and you plug it in to the parentheses, what do you get in there? You get 2 pi. So t gets to 6 pi, but the cosine only feels 2 pi for the first time. And that's the first cycle. Okay, so in general, like what did we do? Let's see, we multiplied by 3. Said another way, we divided by 1/3. In general, the formula is just here in number 16, Melissa. Yeah, so using the formula, if you just like formulas, 2 pi divided by the absolute value of b. B is the number touching the t. How much was b in our example? It was 1/3. So we're taking 2 pi and dividing it by 1/3. Absolute value, because again, if it's negative, you just make it positive right away. And 2 pi divided by 1/3 is the 6 pi that we got before. So that is the period. And I said we would connect this to the stretching compressing idea. If you multiply inside of your function by 1/3, so I'm really thinking of f of 1/3 t, is that a vertical or a horizontal thing? It's horizontal, it's inside. Multiplying by 1/3, is it a compression or is it a stretch? It's actually a stretch. This is the part that I just have to remind myself, anything happening inside the function is opposite of what I think it should be. I feel like 1/3 is making smaller, you're making the t's 1/3 is big, you're not. You need to triple the t's to get what you're expecting. So the function is actually stretched horizontally by a factor of what? By a factor of 3. If I stretch, like say the blue curve, by a factor of 3, what used to happen between 0 and 2 pi now doesn't happen until where? Until 6 pi. So that blue thing would really, really get stretched out to the right. Okay, let's try 17. Where are we now, Topher? Okay. What is the amplitude? Remember, amplitude is the thing we called A. It's the number sitting in the front. It is 1. Let's write down the midline. It is the thing we are calling K, which is the thing added to the end. What is it? 0 in this case. So y equals 0 is our midline. The next important thing for us is the period. You can figure it out, or we'll just practice with our formula. It's 2 pi over b. How much is b? Yeah, b is this 2, and make it positive if it's negative. So b is the number touching the t, which is 2. So the period is pi. Okay, so we're going to draw a complete cycle. It's only going to take pi instead of taking 2 pi. All right, I want to find my 5 important points. I'm going to say something now about cutting up the horizontal, because for the first time we're messing with the horizontal. The 2 things up above were both vertical things, right? We talked about stretching vertically. We talked about shifting vertically. For the first time, we're talking about horizontally, stretching or compressing. And I think things get tricky here. So I take it slow, and I think about cutting up this 0 to 2 pi. That was 1 period. I cut it up into, how many pieces did I cut it into? Is it 4 pieces? I have 5 dots up there, right? But really, how many pieces does that graph have? It's got 1, 2, 3, and 4, right? 5 dots, but 4 pieces to the graph. How do you see those 4 pieces in your unit circle? Those are the 4 quadrants. So all you're doing is you're plotting 4 pieces. The first piece right here, that's the quadrant 1 angles from 0 to pi over 2. Those are your quadrant 2 angles, quadrant 3 angles, and then finally quadrant 4 angles. 5 points, 4 pieces. I think it's really important to take the period, 2 pi, cut it into 4 equal pieces. Let's try that down here. Cut the period into 4 equal pieces. How much was the period for this example? Period was pi. So I'm going to write here period over 4 is how much? Pi over 4. Pi over 4 is my fundamental unit on the x-axis. Okay, that actually works out pretty well for the given sketch, because how much is each of these vertical lines, aren't they? Yeah, isn't this? That's pi fourths. That's 2 pi fourths. That next one is 3 pi fourths. And then finally 4 pi fourths is just pi. But even if it didn't work out nicely, I would still need to focus on those pieces. Pi over 4 are my 4 quadrants. All right, and I think we're good. So let's start marking the graph. Does sign start at the origin, or does it start at the top? Sign is at the origin. Doesn't move at all. The next point gets up to 1. Normally, we don't get there until pi over 2, but now we get there at pi over 4. That's the first part of the graph. I'll draw here in green. These are now my first quadrant angles. It's kind of misleading because 0 to pi over 4, is that the entire quadrant? No, it's only half of the quadrant, but I'm still thinking of 4 pieces to my sine graph. And where's my next dot? Let's see, up at 1, next one must be down at 0, next one is at -1, and the last one is back. So can you guys connect the dots? And then draw a second period, because I think we can fit it in there. You guys draw 2 copies of this thing that I've started in green. So if we put a 2t into the function, is that vertical or horizontal? It's horizontal. Is that a stretch or a compression when you times inside there by 2? It's actually a compression. Weird, I think it should be doubling. I think we should be stretching, but it compressed. Do you see it? You see it, right? Like it just looks more smushed than that one does up there. Any questions on that? Okay. On the next page, we've got one last example to do together. Can I say that that even at the end of this example, we're still leaving out an important transformation. So vertically, we did two things. We stretched or compressed, and we shifted. Horizontally, we stretched or compressed. What do we still have to do? We still have to horizontally shift. So we have not shifted horizontally at all. We also have not reflected. You guys will think about reflections in the homework, but those are pretty straightforward, I think. The horizontal shifts are something that are still coming. So we'll deal with those soon enough. Let's try 18, Kelsey. Okay, so for me at the start, I think of my amplitude, I think of my midline, and I think of my period. What is the amplitude? 3, just the number sitting in the front. It's always the amplitude. Remember the midline is the plus k that sits at the end. 0. I always like to make it y equals. The period is the new part. It requires calculation. It's 2 pi divided by b. 2 pi divided by pi over 5. Turns out that's a nice number. It's 10. Make sure you can figure out that that is 10. Okay, and then the last thing I do before I start drawing is take my period and divide it into how many equal pieces? 4. Always cutting it into my 4 quadrants. So 10 fourths, or 5 halves, or 2.5. Every 2.5. Those are my important X moments. Okay, so I'm prepared to start graphing. How high is this thing going to get? Or actually, maybe we'll draw the midline first. What is the midline? Is it y equals 0? I'll draw it dotted, but it's the x-axis. And then the amplitude was how much? It was 3, which means it's never going more than 3 above. So I'm actually going to draw another dotted line up there at 3, and one down here at -3. I know that my graph will live entirely inside of that band. And what's the first important horizontal number? Yeah, what's the first important horizontal number? Yeah, so 0 will be the first one. And then what's the next one? It's 2.5. Those are the ones I want to mark. But I don't want to mark them randomly. I'd like us to get this to scale if we can. Let's try. Let's see. So if I put 3 up there, then I'll go ahead and try to mark it as 3 equal spaces. So let's use that same scale. Like you can change the scale on the axes if you want to, but let's go ahead and try using the same scale for both. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and now I'm really going to go out of my way to mark the 2.5 points. So the first 2.5 is right there. If I go another 2.5, what number do I land on? That's at 5, so that one happens to be already marked, but I'll label it with a 5. Another 2.5, 7.5, and then the last 2.5 brings me to 10. Where have I seen the number 10 before? Period. Of course, we're going to land on 10 because we've gone all 4 of the pieces. Okay. Then we start plotting points. This is cosine. Does cosine start in the middle or the top? Starts at the top. The top is normally 1. What is the top now? 3. I'll put my first dot right there. The next point for the cosine, if it used to be in the top, what's the next point? Is at the middle, it's in 0. Where do I hit it on the x-axis? At the 2.5. And so, apologies if this is like super slow motion for some of you guys, but I'm just taking it piece by piece. And certainly you can draw things faster than I'm doing here, but for me, I'm grounded by these 5 points, and I really take my time to find those 5 points. Okay, next point. It's either at the top, the middle, or the bottom. Where is it? It's going to be at the bottom. What's the x? Is it 5? So there's my bottom point. Next point, top, middle, or bottom. It's going to be at the middle at 7.5. And the last point is at the top. It happens at 10. And then we connect the dots with a smooth curve. I'm trying. I'm not smart enough to do it complicated. Okay, and the last thing I want to show you guys, after we've done all this stuff here, you don't need to copy this, but I'm going to graph this guy on the calculator. 3 cosine of pi over 5t. 3 cosine pi divided by 5. I don't have t, so I'll put x. And then I'm going to change the window. I'm going to change it because I know what the answer is supposed to look like. What was the first x that I thought was important here? 0. What's the last x I thought was important? It was 10. I'll leave that. What's the bottom y? -3. Top y? 3. Now before I hit graph, Topher had made this kind of funny comment about using the space and using the graph paper efficiently, right? If you pick a good window, how much of the space will you take up? As much as you possibly can. You're going to hit like the corners of your window if you've done this right. So I say that. If I made a typo, I look stupid, but let's try. Topher, seal of approval? Yes. Okay, any questions on that? Oh, that would be fancy. Allie, what does this X scale do? So that's how you make it hit the hash marks. Perfect, thank you. Okay, you guys don't have a whole heck of a lot of time, but can you start by thinking about the problems here in the group activity? And we'll just say have a wonderful break now, and see you when you come back.